In this video, we are going to find positive integers m and n such that m over n plus 1 all divided by m equals 4. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. To solve this equation, I'm going to take a common denominator at the left, which gives m squared plus m plus 1 times n, which is n squared plus n, over mn, and that equals 4. So that means m squared plus n squared plus n equals 4mn. Then at this point, I'm going to make this a quadratic equation of m, which means I have to move 4mn to the left, and then we have m squared minus, let me rearrange the n and m. So the coefficient for the m term is minus 4n, while the so-called constant term, in this case just the term that is independent of m, is n squared plus n. And to find integer solutions, it's necessary for the discriminant to be perfect squared. And by definition, we have minus 4n all squared minus 4 times 1 times n squared plus n. And simplifying, we have 12n squared minus 4n is a perfect squared. However, I can factorize the expression at the left, which gives 4n times 3n minus 1. That's a perfect squared. So in particular, we need n times 3n minus 1 to be perfect squared, because we know 4 is a perfect square already. We can further decompose this equation by noticing that the greatest common divisor, or in short, the GCD of n and 3n minus 1, is actually equal to 1, because we know that any prime factor that divides, say, n, any prime factor that divides n also divides 3n, but not for 3n minus 1. And so that means they must be coprime. Or we can achieve that by using the so-called Euclidean algorithm that should equal to n and minus 1, by just putting away the 3n using the Euclidean algorithm. Now this fact implies that we don't simply have n times 3n minus 1 to be perfect squared, but each of them, n and 3n minus 1, are each being perfect squares. So therefore, n is a perfect squared, and more importantly, 3n minus 1 is a perfect squared. Now from this, notice that 3n minus 1, by definition, is congruent to 2 mod 3, simply because it's a multiple of 3 minus 1. But any number that is congruent to 2 mod 3 cannot be a perfect square. So all of these information implies that the given equation actually has no solution, or no integer solution. So this is the conclusion to this question. Please feel free to share ideas in the comments. Thank you for watching. See you next time.